starting the new lesson. Also that for anybody who needs to go back for this math, you can go back and get it. I'm pausing for just a little bit longer, and then we will move into our final lesson. Woohoo! For Unit 3. There are technically 7, but I'm trying to condense it into 6. Probably 7 units. Probably 7 because I'm condensing another. So we are technically not yet quite halfway through. We'll be halfway through once we get into organic chemistry, right? Which will be starting in December. We'll be starting organic chemistry officially. And we'll be there for a long time. Because organic chemistry, I told you how much of the exam it is around usually. Somewhere between 30 to 50% of the entire paper 2 is organic chemistry. It's a lot. So we gotta know it. But it has no math for those of you that are sick of math. So, I mean, it has counting, but other than that, like, it might be a reprieve from what we're doing now. All right, so I have hit record, I believe. Let me just double check one more time that I have hit record. Yeah, I'm recording. This is one that I want to record because I did move this around. This used to be in the final unit, but I put it into where it belongs. Like, this is all about redox, and there's stoichiometry here. So let's take a look at our final part of Unit 3. Just a reminder on a couple of notes about homework. First off, I only held off on your 2 written homeworks because I saw that about half the students hadn't done it. So I'm giving you one more opportunity tomorrow to come to tutoring to do it and turn it in. So after that, I'm going to go through anybody who doesn't have it. I'm putting the 0 in the grade book, and then the maximum you can get after that point is 70. So make sure you're doing those 2 written homeworks. It was the one on stoichiometry and the one on, welcome back, and the one on redox. All the other grades have been put in. You're going to have a lab this Wednesday. It'll be another titration. I know you're very excited. You'll have another titration this Wednesday. It'll be a redox titration, which means instead of transferring H+, we're transferring electrons. But the math is actually exactly the same between a regular titration and a redox titration. Today you'll be receiving the last written homework. That'll be written homework 5. That'll be due at the end of the week. So I'll be grading all of your written homeworks over the break so that you get feedback on those, so you can look at it to study. The next thing is I did post the paper 1 quizzes. I posted them yesterday. There's a lot of questions. I'm going to warn you. There's like 60 questions between the 2. Do not wait until the last day. I'm giving you 2 weeks to go do the quizzes. If you wait until the last day, you might very well get stuck because of the math. You might very well get stuck and you may get a bad score. I'm not going to be extending that because I'm already giving you 2 weeks to do it because I extended the time for the test. So make sure you find some time, build it into your schedule to start working through those paper 1 questions. After today's lesson, you can do any of the questions on there. We'll have covered everything that could be in there after today, okay? So make sure you get started with it early. I know some of you like to procrastinate. Try to get maybe one of the sets done before break and one set done when you come back at the end of break. Organize your time as you see fit. But it's important that you work through those paper 1 quiz questions and you work through them with fidelity. You actually try them because when you get the actual paper 1, it's your practice. That's your best practice. So make sure you're using that time wisely. So let's go ahead and go over our objectives. We are focusing on one group of the periodic table today. Today we're only going to talk about halogens. Halogens get technically their own unit of, they get their own chapter in the textbook, in the Cambridge text. There's one chapter for the halogens and one chapter for group 2. I'm breaking it up into different sections, but today all about the halogens. So that means today we're going to talk about what elements? Chlorine, bromine, and iodine. These are very famous elements. We're going to have to learn all about the halogens today. Specifically, what they want us to know is to know their colors, Not only do you need to know the standard state of these elements, you need to know what color they are, which we'll go over in a little bit. And the trend in volatility. Volatility is a new term. I don't believe I taught it to you yet. It shows up a lot in Cambridge questions, and so I'll be teaching it to you in today's lesson. What is volatile? What does that mean? Interpret the volatility of elements in terms of their instantaneous dipole-induced cycle. Wait, what is that back? What's that? What's that? That's what we call our dispersion. What's another word? It's ID, right? It's our dispersion forces. So explain volatility based on the intermolecular force, which is called dispersion forces or ID. Yes. So let me double check. Yeah, possible. You can get it. All right, next one. Describe the relative reactivity of the elements as oxidizing. Oh, that's why I put this into here. The reactivity of these as oxidizing agents. Remember what that means? Whatever is likely to be reduced. What's another way of saying what's going to be reduced? What's likely to gain electrons? I bet you already know this. Describe the relative reactivity of halide ions. Halogen, halide. Halide ions would be F minus, Bl minus, Br minus, ions. Those are the ions, right? As reducing agents. How likely are they to be oxidized? And then these are the halogens themselves. Describe and interpret in terms of change of oxidation number. So we have to know oxidation numbers again. This is still redox. We're still in redox. The reaction of chlorine with cold and hot, NaOH. And recognize these as disproportionation reactions, which I realized when I taught redox, I didn't explicitly define what this was, so I'm going to do it today. And then 11.4.2, explain, including by use of equation, the use of chlorine in water purification. So we need to talk about how chlorine works in water purification to purify water. Yes. You're going to have to fill in as you go along for the words that are missing. I mean, I have a couple other copies so you can see if there's a better one. Because I printed a couple extras. Alex, we'll take a look. That's what's printed. All right, we're going to get started. Here we go. So group 17, this is group 17 of our periodic table. We call these the halogens, are all nonmetals. We know that nonmetals have high electronegativity. What does that mean? They attract electrons very well to themselves. You've actually learned that fluorine is the most electronegative element, right? That it goes FON, F-O-N. And actually the next one after F-O-N is Cl. So fluorine, bromine, and iodine, you should know their relative placement to each other in the periodic table. We know that fluorine is the most electronegative out of these. Which means what? Most ability to attract additional electrons. And then iodine then would be what? If fluorine is the most electronegative, iodine is the least electronegative. Which means the weakest, the least ability to attract electrons. Does that make sense too? Least ability. It still could do it, depending on what it's combined with, but it's got the worst ability to attract electrons, the lowest electronegativity. And so, things you need to know about halogens is when a halogen forms a compound. So, for example, I put sodium with chlorine together to form a compound. What happens to chlorine in comparison to sodium? Does it gain or lose electrons? What happens when Na combines with Cl2? What do you make? What type of reaction is this? It's called synthesis, right? You make salt. You make Na, which has a +1 charge, and chlorine, which has a -1. Yeah? So what happens to chlorine in comparison to sodium with its electrons? We know that it's going to gain electrons and that the sodium would lose the electron in comparison. And so that's what it's saying here. All of your halogens, when they form compounds, they tend to gain electrons, become reduced, or serve as the oxidizing agent. Confusing words because it's always backwards for the agent. Memorize that. They're all nonmetals, all your group 17 elements. They all exist diatomically. What does that mean? They all exist as 2. And that's something you definitely need to know. When that element exists, it exists as 2. And they all have a single, I spelled that wrong, and for some reason you never corrected me. All have a single covalent bond. Does it make sense why there are no double bonds or triple bonds? Let's write out F2. Does it make sense why it has to be a single bond? Why? Well, we follow the octet rule, right? And according to the octet rule for most atoms, they will need to have 8 valence electrons. Fluorine has 7, so it only needs 1 bond to add 1 more electron. And if you put any more bonds, that will be wrong, because then we'll have more than 8 electrons, and that's not okay. There's something else we should add in here. All of your halogens have a specific type of intermolecular force. What is it? They all have dispersion force. Or IgIg, right? And why do we say that? Because they are nonpolar. Because they're the same element connected to itself. So they are all nonpolar. More info about halogens. So in their natural state, they exist diatomically. They have dispersion forces, and they have single covalent bonds. What are you going to have to add now into knowledge about halogens? It said you have to know their color, how well they gain electrons in comparison to each other, how well they lose electrons in comparison to each other, that kind of thing. So that's what we're going to go into today, physical properties of the group 17 elements. Now, I know that this didn't copy well for some of you, so please fill in whatever got messed up, because you actually have to memorize the observed colors. You do not have to memorize the radius, the melting point, or the boiling point. However, you do need to know the trend and why the trend is what it is. But you do have to memorize the colors. Now, there is a little bit of a trick to memorizing. They get darker as you go down the group of the periodic table, meaning that fluorine is the lightest. It's almost colorless. It's a very pale yellow. And then chlorine is like a yellowish green. Bromine is an orangey brown. You can say either color if there's a slash there, by the way. Campers would accept either color. And then iodine is the darkest. And we're going to look at iodine on Wednesday because we're doing a titration with iodine. But it can exist as a gray black solid, a purple vapor, or a dark brown liquid is how you'll probably see it. It could be a dark brown liquid as well, which you should write down because that's exactly how you're going to see it on Wednesday's lab. One way that a long time ago that I gave students to memorize bromine is bromine is brown. Bromine brown is the way to remember it. Silly things that hopefully stick. And that they get darker as you go down the periodic table. So the lightest color will be fluorine, and the darkest color will definitely be iodine as you go down. So then there's a couple of explain questions here. Why does atomic radius increase going down the group? Uh-oh. Why does atomic radius increase going down the group for halogens? Or for any set of elements down a group? Go ahead. What are the electrons located in? More energy levels, right? Greater distance between the nucleus and the valence electron. Because there's more energy levels. Between nucleus and valence electrons due to more energy levels. As we go down the group. Why does the melting point increase down the group? So you're given here the melting point of different halogens and the boiling point of different halogens. And you were actually asked to memorize, you probably don't remember this, but you were asked, because I've asked you to memorize a lot, you were asked to memorize standard states, which is something that I asked you to memorize in pre-ACE as well. And you're supposed to know that fluorine and chlorine are gases, bromine is a liquid, and iodine is a solid. That's actually proven in here with the melting points and the boiling points. I'm going to show that to you shortly. But why does the melting point and technically the boiling point increase down the group? What is the answer we have to give when we talk about melting point? Do you remember? Because this class, it circles a lot, meaning we go back over things we should have learned back in Unit 1, Unit 2, which is why you're constantly reassessed on it. What do we talk about when we talk about melting point? Whenever you see melting point or boiling point, you should be talking about the strength of the intermolecular force that holds them together. So you need to talk about, so when you underline melting point, and I'm going to write on the side, IMF. Remember, Cambridge doesn't accept IMF, but this is just the shorthand for you to know what you need to talk about. So what's we going to say? Between fluorine, chlorine, bromine, iodine. Why does the melting point increase down the group? This is fluorine, this is chlorine, this is bromine, iodine. What specifically is increasing down the group? Not enough to say intermolecular forces, though. I just gave you that as a guide. You have to note that the intermolecular force is dispersion, right? And what affects dispersion forces? The amount of electrons. So the way to answer the question is that as you go down the group, there are more electrons in elements further down which increases the amount of energy needed to separate the molecules. Remember, the process of melting is changing a solid to a liquid. So you have to talk about the force of attraction, which is dispersion. You have to talk about what affects it, which is the amount of electrons. And then whenever you talk about why does it increase, you have to say that because the intermolecular forces are greater, it requires more energy to separate the molecule. Come on. Sit down here. Okay, now, before I move on, let's talk about that melting point, boiling point a little bit more. Let's make a number line on the one. What is standard temperature and pressure? What is standard temperature in Celsius? What's standard temperature in Celsius? Anybody know? We did go over ideal gas law not too long ago. 25 degrees Celsius. 25 degrees Celsius is around what we call room temp and standard temp. It's in this area. The reason why I'm bringing this up is because let's take a look at 25 degrees Celsius. Look at fluorine. What is the melting point of fluorine? What does it say there? Negative 220. Is that before or after 25? Before, right? So it's melted before you get to 25 degrees. What about the boiling point of fluorine? What's that? Negative 188. Is negative 188 before or after 25? So fluorine boils at negative 188. What's the state of matter of fluorine at 25 degrees room temperature? That's a gas. Fluorine's a gas, right? Experimentally, it's a gas. Now let's take a look at fluorine. Fluorine melts at what temperature? Meaning it turns from solid to liquid at what temperature Celsius? Is that before or after 25? Before. Okay. Fluorine boils at negative 35. Is that before or after 25? In a number line. Before. Which means the state of matter of chlorine boils at negative 35. So at 25 degrees Celsius, which is how we measure everything for standard, like standard state, we talk about at 25 degrees Celsius, will chlorine be a solid, liquid, or gas? It boiled at negative 35. So chlorine would be a solid. Oh. It's a solid before negative 101. Chlorine's going to be a gas. This is a gas. Chlorine is a gas. What about bromine? Yeah. Bromine melts at negative 7. Bromine melts at negative 7. Bromine boils at 59. Where's 25? It's in the middle, right? So if this is where it turns to liquid, between 7 and 59 would all be liquid, right? Between negative 7 and 59. Remember, the way that it works is it goes solid, liquid, gas, melting point is between solid and liquid, and boiling point is between liquid and gas. So if you're at a melting point of negative 7 and a boiling point of 59, 25 degrees is in the middle there. Bromine is a liquid. And iodine melts at 114 degrees Celsius. At room temperature, like standard state, for iodine should be a solid. And so you should remember that fluorine is a gas, chlorine is a gas, bromine is a liquid, and iodine is a solid. It says it on this periodic table in the front, but it is something that needs to be memorized. And the reason why iodine would be a solid is what? In comparison to the other elements. Why would iodine be a solid at room temperature versus all the other elements in the group are gases or liquids? What do we answer? Go back to intermolecular forces. Intermolecular forces answer state of matter, melting point, boiling point. Why is iodine a solid? Strongest forces of attraction holds it as a solid because it has the most electrons. Yes? So what do you need to memorize here? Colors, standard states, and you should be able to draw conclusions about the intermolecular forces. All right, I'm going to skip a slide. I noticed after I printed it that this question comes before I teach what volatile is. So let's talk about what is volatile in chemistry first. And I apologize for this definition. I didn't come up with it. But I know that it ends up being a big source of confusion because of how volatile is used in other contexts. In chemistry and in science, volatile actually means how easily a substance evaporates. What does that mean? Turns from liquid to gas. Do we agree with that? That's what evaporation is? Liquid to gas? So volatile means easily turns from liquid to gas. Well, what would cause a molecule to be volatile, to evaporate easily? Guess what the answer is? Intermolecular forces again. It turns out that the weaker the intermolecular force, the easier it is going to be for a molecule to turn into a gas. So weaker IMF means more easily turning to a gas. The weaker the intermolecular forces are, the easier it'll be for a molecule to turn into the gas phase, which means the more volatile it is. So, what is the trend down the groups? From fluorine to chlorine to bromine to iodine. Do they get more volatile or less volatile? Less volatile. So fluorine is the most volatile because it's going to turn into a gas first. And iodine is the least volatile because it's going to not very easily turn into a gas. So this word volatile, you just got to get familiar with. I know that a lot of people tie volatile to like reactive, but that's not true. Volatile in chemistry doesn't mean reactive. It means how easily does it turn into a gas. So given that I have now explained this, we're going to go back to that paper 1 question on the prior slide. It's a quick question. Let's take a look at it. I'll pause to give everybody this. Oh no. Don't like that. We still have to go through the lesson regardless. I told you at the beginning of class. This is the one class we cannot give up on time. All right, let's answer this question. Can you answer it? It is the more volatile element and why? First of all, can you figure out which is the more volatile of the 2 elements? Fluorine. So we know that it's got to be C or D, based on first column. All right, which of the 2 things here is the correct statement? C or D? Let's see. This is worth the same 1 mark that the Bell work question was worth. How long did this take you to solve? How long did the Bell work question take you to solve? I just always kind of like to remind you of that. Don't treat every question like it's the same. They're all worth the same marks, but some of them are harder than others. Okay, so if I have to yell, I will, unfortunately. This is the reduction reaction. If I have this. Which of these scenarios is more likely to happen? The one at the top or the one at the bottom? Which one's more likely to gain an electron? Fluorine, right? So this is fluorine, because it's more electronegative, is more likely to gain an electron than iodine. So we say that fluorine is more likely to be reduced and the better oxidizing agent as a result. Iodine is less likely to be reduced than fluorine. So you have to compare elements down a group. We're going to continue here. I'm going to give you some time if you were writing this down. Hopefully stop. Yeah. Yeah. All right, so we're going to continue now. Electronegativity is the big thing that ties into redox. You don't have to memorize electronegativity values. However, you do need to know that fluorine is the most electronegative and iodine is the least electronegative, which means that fluorine is the most likely to be reduced and the best oxidizing agent. Iodine is the least electronegative of the group. It will least likely be reduced. And operate as the worst oxidizing agent. The factors that affect electronegativity are the same as the ones for ionization energy, so you should just write that on the side. That's what I wrote, same as IE. For electronegativity, we care about how positive the nucleus is, we call this nuclear charge, and the shielding effect of electrons. So make sure you have that it's the same as ionization. All right, so I already said this, but what do we mean by this? If I've got fluorine and I've got this, in pre-ACE chemistry, we learned about single replacement reactions, and I believe I asked many, if not all of my classes to remember the trend for halogens, that fluorine is more powerful than chlorine, which is more powerful than bromine, which is more powerful than iodine. And what that meant was in a single replacement reaction, fluorine will kick anything out. Any other halogen will get kicked out. And why is that? Because fluorine is the most powerful. So if you've got fluorine approaching NaI, fluorine is alone and by itself, and iodine is currently in a compound with sodium. Is fluorine powerful enough to steal iodine's electron? Absolutely. Fluorine approaches and is like, get out. Bye. Kicks iodine out, right? Goodbye. Fluorine assumes iodine's position in the compound, and what is our result? What do we get? NaF plus I2. Balancing is 2 and 2. So far, are you following me? Fluorine steals iodine's electron. So what does that tell us about fluorine? It is reduced, which means it is an oxidizing agent. And iodine is oxidized, which means it's a reducing agent. You should write that down. Now, let's say iodine approaches chlorine. Second example. Iodine approaches chlorine. Iodine, lonely, trying to take chlorine's position. Sodium, does it happen? Is iodine strong enough to steal chlorine's electron? No, it's less electronegative than chlorine. It ain't doing anything. So what would the answer be here? In previous, I would have just said, and I'm telling you now, this ain't happening. Not gonna happen. Because iodine is not powerful enough to kick out chlorine, which means that iodine is a terrible oxidizing agent. That's the new terminology that Cambridge wants us to be comfortable with, is using this terminology that iodine, it doesn't replace, so it's not able to oxidize chlorine. Just to be clear with our terminology, why doesn't this happen? Not able to oxidize chlorine, terrible oxidizing agent. Yes? Kind of so far so good? You do need to memorize this order for single replacement reactions. It is actually something that I believe I asked you to know in pre-ACE because it's easy to remember. Fluorine is the most powerful and replaces everything. And then it goes chlorine will replace everything except for fluorine. And then iodine can't replace anything in a single replacement reaction. Now, this is exactly what I just brought up. The order of reactivity: fluorine, chlorine, bromine, iodine. Fluorine is the most powerful, will replace any element. Now I want to bring up something. And it's annoying. I'm prefacing it by saying it's annoying. Cambridge will often show you what's called the ionic equation, meaning that they often won't show you this. What will they show you instead? They'll show you F2, and you're going to want to write this down, plus 2Br minus goes to 2F minus plus Br2. Would you read this and see this was a single replacement reaction initially? It doesn't look like it fits the format, but there you just took out the spectators, and it is the format. So this is how a single replacement reaction between halogens can be observed. We'll take a look at it, what this is saying. So rewrite this without the sodium. What is this called? This is called the ionic equation. And what happens with the ionic equation? We get rid of the spectator ion, which means if the whole point of this reaction is fluorine is kicking bromine out, or fluorine is stealing bromine's electrons, was sodium even part of that conversation? Technically not. And so, first of all, does this reaction happen as printed? Can you prove if this happens or not? Fluorine goes from 0 oxidation number to what here? 0 to -1, which means fluorine gains an electron. Does it make sense that fluorine gains an electron and takes it from bromine? Because that's what this is illustrating. This is saying fluorine takes an electron from bromine. That's what we're observing here. Is that something that makes sense? Yes. Totally makes sense, right? Because fluorine is more powerful. Reaction happens as printed. This is correct. Fluorine has displaced bromine, meaning it's taken its place in solution. So that's why we call it a single displacement reaction. You might have heard it sometimes called single replacement, and some people call it single displacement. It's the same thing, replace and displace. And so I wanted to show you, this is actually, this next question, I was altering this lesson yesterday, and this is a very, very recent question, like from the last exam series that they just gave. So this is a hot, fresh off the presses Cambridge question. acting as 1 ml, right? So we squirt a pipette of MgCl2 into a test tube. And we have another pipette of Br2 in a test tube, right? We mix them together. And they tell you the solution remains orange. Why? First of all, what's the reaction that could be taking place? Where should we start? We're mixing these two things together. We would do Br2 plus MgCl2. So far, so good? They gave you the compounds here, so you can tell what type of reaction this is. What type of reaction is this? A single replacement, if it happens. The next question is, does it happen? Bromine approaches chlorine, says, I'm going to take your position. Chlorine says, no. No. Which one's more powerful? Chlorine. So this is not happening. So then how do we explain that? First of all, what observation told us this wasn't happening? Was there an observation given to us that proved that this reaction does not happen when we mix these two together? Bromine is orange. And if the reaction had happened, which it doesn't, but if it had happened, what would the color of chlorine be? Like a yellow or green gas. They told us this didn't happen. That what we had when we mixed these two things together, it stayed orange. So far, so good? So how do we explain that this stayed orange? What do you think is the proper way to explain ourselves? I didn't really like the course because that's melting points and state of matter. It would have to do with their ability to take away electrons, which means their oxidizing potential, pretty much. And so the way to answer this question is that bromine is not powerful enough, right? Br2 is not powerful enough to do what to chlorine? And how would we say that with oxidation? Because that's our topic. We have to say something about its electrons. Talk about the electrons. It's not powerful enough to do what to chlorine's electrons? Right. It's not powerful enough to take away chlorine's electron. Or another way of saying that is not powerful enough to oxidize chlorine. Alternatively, you could have said, or take away Cl minus electron. I'm putting you could have said this instead if you didn't want to say to oxidize Cl minus. Yes. They do require that you state somehow you're talking about what's happening with the electrons here. So you either have to say that it's not powerful enough to oxidize, or that it's not powerful enough to take away the electrons. So it's not going to happen. And you could say due to lower electronegativity, you could go on. This is only worth 1 mark, so you don't have to go on. You only need to make 1 valid point here. All right, so there's a little bit more that you have to memorize here. If you have iodine, bromine, or chlorine, I'm really actually not quite sure where to fit this info because it's like random info. The colors are pretty much the same. If you take iodine and you mix it with cyclohexane, you take bromine, you mix it with cyclohexane, and you're like, cyclohexane? Yes, organic's coming. Don't worry, it's not too long. Cyclohexane. If you want to know what it is. Not really too big of a point here. You're not going to see too many questions. Just if it showed up on a paper 1 to note that iodine is purple when shaken with cyclohexane, bromine is orange, and chlorine is green, which are the same colors that is their natural standard state. So I just stuck this information here, just in case it shows up somewhere on a question. this is definitely a standard that I hinted at in homework questions, but I never put in the word in any questions, so now I'm bringing up the word. It's called disproportionation. So that's a lot of syllables. Okay, 6 syllables. Wait, are we supposed to have a fire drill today? We should be having a fire drill shortly. It says the 13th. Well, expect that it's possible we get a fire drill at some point. Just to remind you about fire drills, if we get called for a fire drill, we go out that way. Because they're working on the roof, they built the stuff out here for the roof. So we go out to the front door. We did last month, because it was in this class period. So we go out that hallway. And it's happening. If they call for it today. I don't know if they're rescheduling it. All right. CL2, disproportionation. What this means, this word, is that the same element is oxidized and reduced. So in a chemical reaction, you've got the same element being both oxidized and reduced. This can only happen if you have more than one atom of that element. Let's take a look at it with this reaction. The chlorine and sodium hydroxide reactions are definitely examples you've got to, unfortunately, memorize of disproportionation. Just like the thermal decomp reactions, these actually Cambridge asks you to rehearse these, like to know by heart what is the reaction of chlorine with cold sodium hydroxide versus chlorine with hot sodium hydroxide. So this is going to go on your list of I need to know these things. All right, so what is the oxidation number of chlorine on the reactant side here? Oxidation number. How do you get it? It's an element in it. Standard date. So this chlorine will be 0. Do you agree? Are we okay with that being 0? We remember this? What is the oxidation number of chlorine in NaCl? In NaCl, what's the oxidation number of chlorine? Or what's the charge of chlorine? If sodium is +1, then chlorine is -1, right? Check to see if that's about the fire drill. Okay. What's the charge of chlorine, or the oxidation number of chlorine in NaClO? It's -1 in NaCl, but what is it in NaClO? Can you figure it out? Remember that the oxidation number for everything adds up to 0. You know sodium has to be what number? +1, based on its group of the periodic table. What's oxygen's oxidation number got to be? -2. So in order for everything to equal to 0, what does chlorine have to be? 1. So what happens in this reaction? You've got chlorine starting with an oxidation number of 0, and one of the atoms turns into an oxidation number of -1, and the other one turns into an oxidation number of +1. What does that mean? Chlorine has been oxidized, and chlorine has also been reduced, because the charge of one chlorine went up and the charge of another chlorine went down. Whenever you see the same element is both oxidized and reduced in a chemical reaction, this is called disproportionation. That's the fancy name. For one element has been both oxidized and reduced. And you're supposed to trace this by getting the oxidation numbers for the elements on each side of the chemical reaction. Now, I do want to repeat again, and it is unfortunate for you, that Cambridge wants you to memorize the reaction, like straight up, like with the thermal decompositions, you need to put this into your memorize section. They want you to memorize the reaction of chlorine with cold sodium hydroxide, and they want you to memorize the reaction of chlorine with hot sodium hydroxide. I'll give you a little quick way that I memorize it after I go over both of them. I'll tell you what I do just to memorize Beforehand, take a look at this paper one question. And then see if you can solve it and tell me if you found it to be easy or difficult. Four equations represent reactions of nitrogen. Which one is disproportionation? Go ahead and go over it and see if you can come up with the answer, and then we'll assign a level to if you think this question is easy or difficult. Go ahead and go through them. Which one of these, only one of these is disproportionation? Gotta know oxidation numbers. Solid. If you have it, raise your hand and I'll check it. We're pausing for you to do a question before moving on. Which of these is disproportionate? Which one of these is disproportionate? Work out the oxidation numbers. Let me stamp it. Can I check for stamps? Yeah, I blame the printer at the school. It's the copier, because like the original copy is clear. I have a new ink cartridge toner coming in the mail. Yeah. For ink for print, because I usually print all the stuff at home for these classes. One of the copiers at the school is missing. That's correct. Good job. All right. Anybody else ready for me to check? Giving you another minute before I go over it and continue. We're almost done with the content. Perfect. Very good. Which of these is disproportionation? Remember, disproportionation means that the same element is both oxidized and reduced on the product side, meaning its oxidation number goes up and its oxidation number goes down. There's a couple of examples there you could take out immediately based on this knowledge. All right, 30 more seconds. All right, so first thing I want to bring up, are any of these reactions not redox at all? Remember, double replacements are never redox, ever. Which actually means, if you look at this closely, you could take out A, because that's the H2CO3 that breaks up to CO2 and water that we're supposed to remember. You could take out A. You could technically also take out one more. See? Because this makes ammonia breaks up to NH3 in water yet. I will in a later unit. And that's double replacement, right? Because you've got two switches that happen here. So that's out. So you've actually only got to look at B and you look at B. Is that a disproportionation? It's the simplest one. You don't have something the same element being oxidized and reduced because only one change is happening, right? So that doesn't make any sense. It only goes from 0 to -3. The answer is definitely B. Nitrogen here is +4. Nitrogen here is +5 if you work it out. And nitrogen here is +3. Nitrogen goes from 4 to 5, and it goes from 4 to 3. Oxidation number goes both up and down. That's disproportionation. Make sense? The answer here is D. Yes. This I would consider, beyond knowing what the term is, a level what question? I would consider this level 1. I would consider this about as easy of a redox question as I could give you in this topic of disproportionation. All right, we're almost done. Unfortunately, I'm asking you to memorize this equation. This is the disproportionation of chlorine with hot sodium hydroxide. I'm going to be honest with you. The reactions here, they show up sometimes in questions. If you're shooting for like an A-level score, I would memorize them. But if you're shooting for like a C or a D-level score, it's up to you if you want to memorize these equations. There are some random reactions that I just suggest. Just put them on flashcards and at the end of the year kind of like circulate through them. This would be one of those. That there's really no rhyme or reason. It's just you're being asked to memorize this as an example of a disproportionation reaction. Will I put it on the exams? Yes, I still will. But I'm just saying that it's not going to be like all the points of the exam. It'll be a couple of points maybe. But I just want to be honest with you that there's a lot to memorize in this class. This has no further use beyond memorizing it for random stoichiometry questions that may show up on a paper 1 or paper 2 every once in a while. So it's up to you whether you choose to memorize these or not. It is something that Cambridge is asking you to know. They're asking you to know the reaction with cold versus hot. Now, I told you that I was going to show you a way to memorize the two, the difference between the two. I'm going to go ahead and do that now. So, cold versus hot. Just a little bit of a quick way to memorize the two. It'll become more apparent why this happens later on in the year after we get through organic, believe it or not. You'll understand this reaction a little bit more. But right now, this is what I would memorize. Cl2 plus NaOH. Cold actually means less oxygens versus hot means more oxygens. So with cold, your three products are NaCl, NaClO, and water. That's your cold reaction. The only difference between the cold reaction and the hot reaction is that in the hot reaction, you end up with more oxygen in your product with the polyatomic ion. So instead of NaClO, you end up with NaClO3. The other two products are exactly the same. So I want you to note the key difference. And then obviously you'd have to balance the equation from there. But I would just memorize the template for the equation and then balance the equation after that. The difference between the two, they both have three products. Both of them make salt and water. The one that's a lower temperature only gives you one oxygen in the polyatomic ion. The one that's a higher temperature gives you 3 oxygens in the polyatomic ion. That's the way that I memorize the difference between the two equations. Why does the one that's hotter have more oxygen? That's something we're going to answer when we get to organic chemistry, because there's a whole week of redox in organic chemistry. I know you're all so very excited for more redox, but it'll answer why when we get to that. For now, I would just say memorize these. It can show up. You're going to need these equations for the quizzes. If they mention cold alkali, remember alkali is the same thing as base. You may see them use the word alkali instead of saying NaOH. Remember, alkali means base. So you may want to point that out. All right. This is the reason why. Take a look at this paper 1 question. It tells you reaction of bromine, warm NaOH, is the same numbers and the same ratios as chlorine with hot NaOH. In one reaction, you get 30.2 grams of a product that contains sodium, bromine, and oxygen. What's the mass of NaOH? This is literally the same type of question you had in the bell work, isn't it? It's literally the same type of thing they're asking. But instead of giving you thermal decomposition, this time they're giving you what? The sodium hydroxide reaction. They made this more complicated by, instead of giving you chlorine, they're giving you bromine. And they're asking you to basically use this reaction as a template. And instead of chlorine, you're going to replace it with bromine. So let's go ahead and do that. Start with the reaction. It's 3Br2 plus 6NaOH, because it's hot is what we're looking for. So we're looking for the equation for hot. 5NaBr plus NaBrO3 plus 3 waters. That's the reaction. 36513. So that's the equation. Once you have the equation, this is just simply called stoichiometry, right? Where they're making this question difficult is they're making you come up with the reaction. Once you have the reaction, this is a grams to grams question. This is the same thing you saw in the bell work. They're giving you 30.2 grams of a product that contains sodium, bromine, and oxygen. Which product is that? The NaBr, the NaBrO3, or the H2O? It's this, right? This is what they gave us 30.2 grams of. And what are we looking for? What are they asking in the question?
The mass of NaOH.
Which means we are looking for this in grams. So this is a grams to, well, it's just a grams to grams question, right? So all we need is the relative molecular mass of NaBrO3 and the relative molecular mass of 6 sodium hydroxide. Can we get that? All right, let's pull the relative molecular mass of NaBrO3. I did it earlier. Please check me. I got 150.9 NaBrO3, which is 23 plus 79.9 plus 48. See if you get the same number. I got 150.9. That's my MR for NaBrO3. And then for 6 sodium hydroxides, what do you get? I've memorized that sodium hydroxide is 40. Just used it so much. It's 23 plus 16 plus 1. So sodium hydroxide is 40, but you multiply that by 6, you get 240 grams. And so that's the ratio that we need. We have 30.2 grams NaBrO3. So what number do I divide by?
150.9.
And then I multiply by?
240.
Yeah, that's correct. And I got 48 when doing that. Check the math to see if it's the same thing. Just simply divide by the mass of NaBrO3, multiply by the mass of the 6 NaOHs. You could not get this right, though, if you didn't memorize the equation. So, unfortunately, this is one of those questions that you have to make a decision. Are you going to memorize random reactions or not? This is one of the random reactions you may see on a paper 1 or a paper 2. We're almost done. You're so almost done. The last slide is technically the last slide that's in the standard for today, but I'm going to talk about the last thing. Let's hold because just in case the fire alarm rings, I don't want you to get stuck. I don't know if it's being rescheduled or not. Sorry. Okay, last standard. It's a pretty easy one. If it shows up, this is just going into your, hey, I need to know these things. Over the years, Cambridge has been, unfortunately, or fortunately, depending on how you think of it, Cambridge has been taking out this type of standard. Meaning a lot of the environmental type standards have been gutted out of the class. Meaning this is one of the few that's left that you have to remember. And so this is the process of chlorinating water. And Cambridge wants you to know this process. And if you look back at the standard, it says they actually want you to know the equation. So this is the chemical reaction that kills bacteria, actually. So when chlorine's added to water, which is, you should hopefully know that that's what they do in pools, right? You put chlorine in pool water, and what that does is it kills the bacteria. Where does the bacteria come from? Our skin. Some people use the bathroom in the pools. And so this reaction is intentionally done. They add chlorine to pool water. My friend does this actually for a living. That's like his whole job. Because he goes and he cleans pools as his life. And he does this basically, he doesn't have to know the reaction by heart, but he knows he has to add the chlorine to the water. And it makes this. What are these products? This is hydrochloric acid, isn't it? So just so you know, there's some hydrochloric acid in your pool water, and that helps neutralize the bacteria. But the main part, the important part, is this, the HClO. HClO in the sun will decompose slowly to literally make this. Like literally the oxygen breaks off like this. And you get HCl and you get oxygen. But that oxygen is crazy. That's not normal oxygen. What's wrong with this oxygen? It's not 2. Trace those valence electrons. This oxygen is what we call a free radical, which I believe I mentioned earlier in the class, but we haven't really done too much with it. We're still not going to do too much with it until we get to organic. We're holding on organic for that. But it's a free radical, and it is very not stable, which means it attacks anything it can. What do we mean by attack? Oxygen wants what? It's going to take electrons from anything different. So if there's bacteria, it's like, I'm going to steal your electron and then it destroys the bacteria. Kills the bacteria, basically, by stealing its electrons. Oxygen. Angry oxygen. Free radical oxygen is angry oxygen. Will steal that electron. So it kills the bacteria, destroys the bacteria, because it is in an unstable state. So yes, Cambridge does want you to know these reactions. I think they're actually rather interesting. You add chlorine to cold water. What happens as a result is you get hydrochloric acid and HClO. HClO is actually also a component of bleach. Then the HClO under UV light, under the sunlight, breaks apart to make more hydrochloric acid and this really reactive alone oxygen. Not diatomic oxygen, not the type we breathe, not ozone oxygen, which is in the top layer of the earth, but just a single atom of oxygen. And that is not normal. That is not stable. And it is angry. And it attacks. It reacts and destroys the bacteria. And that's why you add your chlorine to your pool water. And I actually wish Cambridge had more of these types of standards in here because they're interesting. They're interesting factoids. But this is a factoid standard that Cambridge could ask you on a paper 1 or a paper 2. It's the last one. I left this stuff in here because I saw paper 3 recently that brought up bleach. Bleach is a mixture of these two. And bleach will actually oxidize. That's its purpose. It oxidizes colored molecules by doing what? Taking their electrons. So Na, this mixture of NaCl and NaClO will bleach colors by stealing their electrons in different colored compounds. So this is kind of cool. Oxygen's being a menace again in bleach. Bleach you use, some people use for their hair, but you should be aware that if you bleach your hair, it really messes it up because you're putting free radical oxygen again in your hair. So it does mess it up. And that's why when you do, if you do bleach your hair, you need to use like a lot of conditioner. You need to use a lot of good products to make sure that your hair isn't like strong as a result. I know my mom used really cheap products and it was and she bleached her hair her whole life. But anyway, so other uses, halogens can be used in PVC piping. You're not going to see this again until we talk about organic. This is going to show up in organic chemistry. So I just left this because it wasn't a later part of the year. In PVC and as solvents, refrigerants, and aerosols. All the purpose of these halogens are usually to kill bacteria. Halogens are also used in non-stick pans and in fire extinguishing. Halogens are used in fire extinguishing. So they have a lot of uses. The main one you have to know for the purpose of what I'm testing right now is chlorination of water. That's the standard that I'm testing right now. So you have to memorize those reactions. You may see bleach show up in questions here or there, but just know that it's the same idea of what happens with the chlorination of water, that oxygen stealing electrons, and it decolorizes, meaning takes the color away. All right, so we're about done. We're done with the unit technically. I have your homework. You're welcome. I believe your homework printed out well because I used the other copier. You're welcome again. Homework is due Thursday night. Don't forget, if you have homework missing, tutoring is tomorrow. That is the last tutoring before we go to break. And then we'll have one more when we come back from break on that Tuesday. I will be grading any of your written homeworks that I haven't graded over the Thanksgiving break on the Sunday. That's how I work. So on the Sunday, make sure that you get everything done so that I can give you feedback on your work. All right, before you take the test. And don't forget your paper 1 questions. So you can start working on those at any time at this point. Finally, next class you have you have another lab next class. So we're done with content for the unit. When we come back from break, we'll review. We'll spend one day review and practice on that period, and then the next class on that Thursday, we'll have you for unit 3. I gave you this already? It looks like. Final written homework of the unit. Final written homework of the unit. Final written homework of the unit.
What were you doing on
That's so weird. They didn't come for
I heard. Right, don't speak.
Good afternoon, Go Lions. This is Supervisor here. Students, please remember to check your parents' email daily and report to school with proper CIE uniform. Make sure your outwear is solid white, black, or red. Also, remember your 290 status. Yes, the issue the 2 to that. Please remember that you must wear your student ID every day. Lost your ID, cover with Bring your placement ID y mantén fuera no OSP. Due to unpaid balances and not be allowed to